Welcome to this forum. This global networking forum organized by the Mexican Space Agency on disruptive space technology will address how disruptive space technology is transforming our world, mainly around small satellite platforms. On behalf of the Mexican Space Agency, it's a pleasure and honor to introduce you Andres Martinez from NASA headquarters. He's the Program Executive of Advanced Exploration Systems, Human Exploration and Operation Mission Directorate. So please welcome him with applause.
Thank you, Blanca.
Thank you.
And thanks everyone for attending our forum here. Buenas tardes, bienvenidos a Guadalajara. What I'm going to do is I'm going to just open up with a few remarks, then I'm going to introduce our speakers. Each speaker will say a few words about this topic. We're going to be interjecting with questions as we move along. And then towards the end, we're going to open up for questions to you guys. All right, so over the past few years, we have seen a significant increase in the use of small satellites, both for operational applications and also to conduct science experiments. Missions traditionally meant for much bigger spacecrafts we're now conducting with these tiny little small satellites. We have also seen an increase in the use to demonstrate new technologies. The program I was previously leading, that's all we did. We developed and tested in space new technologies. And also for educational purposes. The miniaturization of key critical technologies and the advancements that we are making in these technologies required for complex missions, the advances we've seen in the past few years have moved at a very fast pace. Project teams are also now more agile, working smarter with more mature engineering methodologies, tools that have advanced significantly, and test facilities with lots and lots of automation wherever this is required. The availability of these technologies, coupled with a greater access to space provided by both commercial vendors as well as government programs such as the CubeSat Launch Initiative, now has resulted in the proliferation of small satellites that actually make it to space. We've now reached a wider small satellite development audience and have grown this community significantly. From the traditional space organizations within government agencies to commercial industry and academia, we've seen a growth that it is unprecedented. Not long ago, we celebrated when a university first built, launched, and operated a small satellite mission. This made the news. But soon after, a high school would also do the same. And it was followed shortly by a middle school. And just a couple of months ago, an elementary school did that as well. Overall, across the board, we have seen some pretty amazing experiences and accomplishments by the team members of all of these projects. In this panel, we will touch on the disruptive space technology with a focus on small satellites. Now let me introduce our speakers. To my right, we have Dr. David Korsmeyer. He is the Director of Engineering at NASA Ames Research Center in Silicon Valley, California. He is a strong advocate for small satellite and nano-satellite missions, with NASA Ames flying more than 26 in-house small sats over the past 10 years. In addition, he has developed novel software and systems for the Mars exploration rovers, the International Space Station, and for the Kepler mission search for exoplanets. He is a member of the IAC Space Exploration Committee and a NASA senior executive. He has a PhD in astrodynamics from the University of Texas at Austin and has a master's in management and is a Sloan Fellow at the Stanford Graduate School of Business. To my left, we have Sir Martin Sweeting, who has pioneered rapid response, low-cost, and highly capable small satellites utilizing modern consumer electronics to change the economics of space, and is the founder and executive chairman of SSTL that has built and launched 47 small satellites, as well as the 22 satellites navigation payloads for the European Galileo constellation. Sir Martin also chairs the Surrey Space Center, investigating advanced small satellite concepts and techniques, which acts as a research laboratory for SSTL, an exemplar of real academic commercial synergy. Sir Martin is a fellow of both the UK Royal Society and the Royal Academy of Engineering. He is a distinguished professor at the University of Surrey, and in 2014 was identified by the Sunday Times as one of the United Kingdom's 20 most influential engineers. To my right, we have Robbie Schingler. He is the co-founder and chief strategy officer of Planet. He is responsible for policy, social impact, corporate development, and European activities. Prior to Planet, Robbie spent 9 years at NASA, where he helped build the small spacecraft office at NASA Ames and was capture manager for the Transiting Exoplanet Survey satellite, also known as TESS. Robbie later served as NASA's open government representative to the White House and served as chief of staff for the Office of the Chief Technologist at NASA. He received an MBA from Georgetown University, a master's in space studies from the International Space University, and a bachelor's in science and engineering physics from Santa Clara University. Robbie was a 2005 Presidential Management Fellow. Please welcome these incredible speakers to our panel. And now we're going to begin with Dr. Korsmeyer, who's going to spend a few minutes talking about his experience and how these small satellites are bringing so much disruption to this field.
Thank you, Andres. I hope this is on. Yes. Yeah? Okay. So first, one of the things I was thinking about when Andres first invited me to be on this panel was what truly makes the disruptive space technologies or innovations. And I would first say small satellites, but then I thought about it, and actually Robbie and I even talked about it a little bit, and the truth of the fact, in my opinion, is that it's really the much improved, much easier access to space that is really causing or engendering the disruption. It used to be, and still is, if you're going to fly a significant space system in orbit, you're going to have to spend 40, 50, 60, $100 million easily to procure your own launch vehicle. Then you're going to have to spend all the engine expertise to custom build a spacecraft. Thank you. To custom build a spacecraft, and then you're going to have to spend all of the additional costs validating and making it completely safety and risk tolerant and fly it into space. With the advent of the nanosatellite platform, right, the CubeSat platform, it's not so much that it's exactly 10 centimeters by 10 centimeters by 10 centimeters. Why is that important? It could be 12 centimeters, it could be a foot, it could be any size. The thing that makes it disruptive is it's a fixed size, and it's a fixed sized in a canister. So what they've done is they've allowed the transfer of the risk from the launch vehicle to the spacecraft. Let me explain. By putting it in a box, which is what you're really doing with these small nanosatellites, by putting it in a box, you've taken a lot of the risk concern that a launch vehicle normally would have, because they're going to fly somebody else's mission with a $100 million satellite on it, and they don't want that $100 million satellite disrupted. But they have a lot of extra, 10, 20, 100 kilograms of extra mass. They have cubic meters of extra volume, and they'd love to sell that to you, but they don't want to take an additional risk. So the way to avoid the additional risk is you put it in a box, a nice strong box that if there's an explosion or some pieces fall off, won't disrupt the main satellite. And then you deploy these secondary satellites, these nanosats, after the main mission has already left and is well out of the way and is safe. So that's one big key area. It's the easier access to space, which is afforded to you by having canisterized, uniform, launch capability. You can take that from an Atlas to a SpaceX launch vehicle to the International Space Station. All the same size nanosat will fly on any of those with very, very minor, if no, additional changes. So that two things makes a great change. It's the access to space, the transfer of the risk from the launch vehicle to the satellite. And then the last thing is, I think, because you have those two things, now the ease of access allows lower cost communities like universities, schools, as Andres was talking about, and small companies to much more effectively get access to space. They don't have to buy a whole launch vehicle. They don't have to build a satellite that is guaranteed to work and not harm somebody else's satellite. They can just buy components, put it together, put it in a nanosat deployer box, and launch it for maybe $100,000. That sounds like a lot of money, and it is a lot of money, but it's a lot less than $10 to $100 million. And with NASA's CubeSat launch initiative, which actually allows universities to propose for additional launch opportunities on NASA launch vehicles, it's effectively free. All you have to do is try out, write a proposal. If you get awarded, you build the spacecraft and you can fly it. That's a huge opportunity. So now there's a much larger community of people all trying to do the same thing. Those three things: access, canisterization, larger community.
Thanks, Dave. Can you talk to us about maybe a couple of examples that your organization has led, that you would find revolutionary, either in the science aspects or technology that was being that was developed and demonstrated in space?
Sure, I'll talk about just two. One, Robbie was actually involved in, and he'll talk a little bit about probably, or maybe not, was called PhoneSat. And why was it revolutionary? We effectively, NASA Ames, flew a phone in space. Well, who cares? Except that if you think about it, a phone has a lot of the same capabilities a satellite would need to have. It's got computing, it's got memory, it's got communication, it's got attitude control, it knows what orientation it's in, it's got long-lived batteries. What we were trying to do really, I think, was validate that consumer-grade electronics, commercial off-the-shelf capability, was so mature and so robust, you could actually operate it in space. And we did. We did it several times. Several first iterations of the PhoneSat and then several future iterations of the PhoneSat have flown, and we actually built a swarm of satellites based on that technology, which took commercial satellite, commercial consumer-grade electronics. We did nothing special. We literally went to local stores and bought the parts and then put them together and tested them and did the engineering the NASA way, but everything else was standard. So that was one big one. The other one is we're working on now, for NASA, a bit of a stretch, a deep space nanosat. If you saw some of the talks where they're talking about the very large SLS launch vehicles, we're launching a 6U nanosat, which means it's 10 centimeters by 20 centimeters by 30 centimeters sized, and that's going to go out to 70 million miles outside, past low Earth orbit. That's going to be wildly disruptive. We have never built something so inexpensively that's going to ride as a secondary payload to a main mission that's going to go so deep, and that's going to be a biological radiation sensor. So there's some very cool technologies we can demonstrate at very low cost that otherwise would require hundreds of millions of dollars to develop and buy a launch vehicle to use. We can just fly along on a launch that's already going to happen at a marginal cost, again, very expensive, but we're the government, but really much, much smaller than you would otherwise have to do, and that is hugely disruptive to the standard way NASA does its work.
Excellent. So one of the things that I want the three of you to also consider is, when we embark on these projects, one of the things that we look for also is, what is it doing for the first time? Is there any technological or scientific breakthrough that we're going to be conducting with this mission? And the second thing is there also a commercial infusion, right? From a government standpoint, from a nonprofit standpoint, is there anything that will make its way into the commercial sector that will be available to the entire community? can you just spend maybe a minute or two?
I'll spend one more minute
Yeah.
because I don't want to monopolize.
Yeah.
The PhoneSat team did commercialize. I'll let Robbie talk to that later, I think. And that's a good thing. NASA has the role as a U.S. government agency to engender the space economy for all peoples. And so finding something that is commercially viable and having that become a commercial industrial activity, that's a win. That's a win for the U.S. government. That's a win for NASA. I think that's a win for the broader community. In addition, I think there's we're finding we do a lot of space biology at NASA Ames. There's a lot of very interesting drug metabolism that's done in space that behaves completely different than it does on the ground. We've been talking about this for years, and there's a number of interesting missions that are on the space station now that make use of this. But space station time is very hard to get. It's hard to get astronauts time. It's hard to get all that information that you want in the time allotted. We're now flying very small satellites as free flyers that do those biological things and commercializing that technology.
Thank you. All right. Sir Martin Sweeting, can you also share some of the activities within your organization that you would find disruptive, the projects and how these have progressed?
Yes, certainly. Well, very good afternoon to everybody. And I think it's highly appropriate that for a discussion of small satellites, we have a very small but perfectly formed panel. I would like to step back a little bit, perhaps betraying my academic roots, and just have a look at the overall philosophy of the disruption in space. And it's quite clear that since the early 1980s, small satellites have evolved steadily in their capabilities. And what is really important, and I think has come out in the opening statements, is their utility. And this utility has grown to the point where over the last few years, we're not only producing lower cost and more responsive solutions to meet some of the very well-trodden applications, but at the same time also stimulating completely new business models. And this is fundamentally changing the economics of space for both the civil and the defense and security sectors. And the underlying technologies that have enabled this pretty peaceful revolution, but it is a revolution, have come from the enormous investments that have been made by the industrial and the domestic consumer sectors, and we've heard a bit about PhoneSat, that have created mass markets for their products. And what this has done is it has reduced the unit production costs of particularly microelectronics by orders of magnitude, but at the same time achieving very high levels of reliability. And this has been achieved through a sort of parallel revolution, if you like, in manufacturing and production techniques. And these two things combined together is really the underlying key, because small satellites have been really effective in taking advantage of commercial off-the-shelf or COTS microelectronics to create smaller but lower cost and capable, reliable satellites. However, if you look at it up to the beginning of this decade, the evolution of these small satellites was primarily being driven by the advances in microelectronics, whilst actually the structural designs tended to be based on more conventional techniques. And it's really in the last 5 years that the pace of microelectronics has continued to accelerate, much in line with the observations of Gordon Moore in the 1960s. So we see our smartphones getting more advanced year by year. We have to go out and buy new ones every 2 years. And it's really this combination of microelectronics with the development, parallel development of new materials combined with robotics, which have given rise to a whole new approach to satellite and spacecraft engineering, which can not only reduce cost, but also dramatically reduce timeframes. In fact, in this Congress, we have already seen how robotic additive and subtractive manufacturing techniques can now make possible geometries that were previously physically impossible by human hands, and how digital manufacturing provides a freedom of location and dramatically increases the speed of design evolution and product innovation cycle. These factors have all come together to stimulate innovative new space system proposals, taking advantage of the design agility, the low unit cost, and the rapid manufacturing delivery to make constellations of hundreds, even thousands of small satellites practical, that would enable entirely new infrastructures that providing ubiquitous access to high-speed digital communications and unparalleled persistence of a global Earth observation. At the same time, the growth of these various terrestrial infrastructures have occurred, and the advances in data handling, management, and knowledge extraction, often referred to very much as sort of big data, have blurred now the boundaries between space and the terrestrial systems. And of course, you know, the new mega constellations, if we term them as such, also propose new challenges. Regular, affordable launch on a tempo that's hitherto not been achieved is going to be necessary. Space traffic management and debris control, the efficient handling of communications of vast amounts of data, safe, autonomous orbital operations, and of course not forgetting the pressures that we will have on communication spectrum and some of the allied legal or policy issues. But like the extraordinary number and diversity of smartphone apps that we have seen created by a completely new business community, most of which of these apps we would never have dreamed of a decade ago, it's quite probable that the new small sats and their constellations will stimulate applications that we currently do not even envisage. Only time will tell what they will be. In the coming few years, these techniques, I believe, will continue to advance and enable us to take a totally different approach as to how we create space systems. As we reach the sensible limits of spacecraft, individual spacecraft launch mass and envelope, and actually the limits that we can achieve with origami on things like the James Webb Telescope, we are going to be looking increasingly at in-orbit robotic assembly of large adaptable structures for communications or Earth observation or astronomical observations, in-orbit spacecraft repair in order to extend life, and of course, in due course, in-orbit manufacture of satellites. And this will substantially change the way we approach the design of satellite structures. But you know, finally, if we look thinking about the new applications, perhaps the grandest application of this combination of disruptive technologies and the business models could be to enable the vision that was outlined yesterday by Elon Musk and in the previous session here this afternoon by Jan Werner, of sustainable and affordable human habitation on the Moon and Mars.
Thank you, Sir Sweeting. Also, a similar question. Can you share with us an example where, you know, a past or a current project where your team did a technological breakthrough for the first time, or where, you know, a group of members of your team went out and funded a new company where, you know, technology made its way out into the wider masses?
Well, I suppose if we go back, our company, Surrey Satellite Technology, based at the University of Surrey, spun out just over 30 years ago from a university research team. So it started out as a university project, started in order to progress further. We formed a company, and that company has grown over the last 30 years. And throughout those 3 decades, we have tried to take very different approaches to space. And perhaps the two that I would like to highlight, first of all, was taking advantage of the combination of COTS devices in processing and imaging to create the first disaster monitoring constellation. What this did is taking small satellites, having an affordable constellation allowed us to be able to image anywhere on the Earth's surface within 24 hours and therefore provide much greater responsiveness in the events of either natural or man-made disasters. And unfortunately, there's a natural or man-made disaster about once a week somewhere around the world, so getting rapid response data from that into the community that is trying to mitigate the effects of those disasters was something that only a constellation can provide, and the cost of a constellation. I would like to link in as well, actually, that we also launched a phone sat and to demonstrate precisely the points that were made earlier, which was to demonstrate how we could take these highly condensed systems and to produce very small spacecraft and then think how we could adapt those for various applications. And having the first of these phone sets in orbit was, I think, quite a major achievement.
Thank you. Thank you. One more thing, and this is for the other two speakers as well. So small satellites bring the promise of lower cost missions at a faster pace, but at a higher risk. What is the philosophy of Surrey when it comes to this, and how do you guys approach, the missions when you encounter anomalies?
I would very respectfully challenge the perception that small satellites per se represent a higher risk, because actually we've now launched 50 spacecraft, and of those 50 spacecraft we've had only one that failed, and that was due to the fact that it got stuck on the rocket, so it never made it into orbit. So I think the perception that small satellites are higher risk, I think, is fundamentally flawed. What it does require is a very different architectural approach and a very deep understanding of the technology that goes behind the COTS devices that are being used. Now, if you take random COTS and put the devices and put that into your satellite, the chances are you will be disappointed with the reliability. But if you understand deeply the physics, the manufacturing processes, and construct around it a failure-resilient architecture, then I would say that these small satellites indeed might even have a higher per unit reliability. Thanks.
I appreciate your input. I was referring to the studies that have been made overall on the small sats and the percentage of mission success, which is.
But I think you've got to be very careful. Sorry, I don't wish to.
So that's what I was pointing to.
Let's have a good argument. There's nothing like that. I think you've got to be very careful how you classify it, because if you look at the recent history of CubeSat launches, then the success rate has been rather disappointing. I think something like 60% of those missions have failed. But these are new entrants into the space arena and taking a certain, and without, on the whole, very much background in space engineering and associated topics. A very, very effective learning experience for them. But I think we have to be careful to separate out what is a learning experience and what is intrinsically the reliability of, shall we say, commercial small satellites.
Thanks. Okay, so now let me move on to Robbie Schindler. Similar approach?
Sure, so thanks for this panel. I do look forward to questions as well, so hopefully we can have an engaging discussion. Dave is exactly right around one of the major trends is getting access to space via secondary payloads and having a standard size to allow for payload providers to innovate within. And of course, Sir Martin has actually created this industry. And everything that he's talking about with respect to writing Moore's Law, looking at the spec sheets and understanding each one of the components within of the integrated circuits within consumer devices, adapting them and using the correct ones for the space environment has just a tremendous upswing in capability in a short period of time. I think the thing that I would like to add to this discussion is the fact that when your cost comes down, then you can take a little bit more risk. And if you can take a little bit more risk, then you can learn a lot. You learn a lot from failure, and you also learn a lot from successes. As they actually become successful, with that learning, you then do the next one. Then you do the next one. And so this lends itself, this is actually just speeds up the development curve. If you take a look at like an established aerospace, more traditional aerospace company like an Airbus or a Boeing or Space Systems Loral, they launch and build hundreds of satellites over the history of their company. But it's been over 40 or 50 years. So they learn from each step along the way. But that speed of learning is not every 3 months, it's every 3 years. And because their satellites are much larger and they are doing it for a very specific purpose, They want to ensure that it's going to work, so they inherently buy down a lot of risk by using redundant systems, by using components that they've flown before, and making sure that they model it, test it through and through so that it deterministically is going to perform. So there's something about speed and risk that is disruptive to, inherently to small satellites. It does, but the size doesn't have to do with capability. It really does have to do with cost. It has to, which is access to space. And so that's one thing I definitely want to add within Planet. So I spent most of my career at NASA and learned at NASA a lot about aerospace, a lot about building teams and technology, and knowing that approach on how to build complex electromechanical systems. And one of the projects that Will and Chris, my two co-founders, I actually wasn't working on PhoneSat, by the way, but they were working on was called PhoneSat. And with that, it was finally so cheap that we were actually able to build it. Everything else that we wanted to do, we thought they were cheap, being like $20 million, and that's super cheap in the scheme of NASA, not 200 million or 400 million. But we still couldn't actually build it yet. And so if it's a good technology that they want to validate and verify, or it's a really, really good scientific investigation that is needed by the community, the import goes up, and therefore the budget goes up, the duration of the mission is longer, then before you know it, a $20 million mission is a $400 million mission. And that did actually happen to me on one of the projects I was working on. So by actually being able to just get a small team of people together, understand the entire system itself, where literally you don't have an ICD, you don't have an interface control document between the different subsystems. You have 8 people that are building the entire satellite that you can actually build it in 6 months. That was enough for us to actually recognize that you could build satellites differently. So one thing that we did at Planet is, it turns out a phone in and of itself is not the perfect satellite, but the components within it are super, super good. So when we started at Planet, it was more of a capabilities-based approach, which then you accept more risk instead of a requirements-driven approach. And then with that, we then iterate on it every single 3 months to then get to a very robust system. And that's in fact what we ended up doing at Planet. There are lots of lessons that we've learned within the technology development process that in retrospect are obvious, but we didn't actually know was true. So one learning, for instance, on the satellite manufacturing side is you actually want to have really complex parts and components so that when you then end up putting them together, they only get put together in one way. And if they get put together in one way, then that decreases the rework that you have to do on the line, and therefore the quality of the product as it actually comes out. So that was something that we learned. Before it was very, very simple components, very, very cheap, try to get the unit cost down. But then when you think about the end-to-end system, you realize that no, you actually want to spend more money on a particular part or a particular activity because you're then going to save money later down the value chain. So the speed and the risk, being able to think about the end-to-end system to know where to invest your resources, because ultimately we love the satellite, we love that sensor, but it really is about the information that you're going to gather from the sensor. That's the reason why you're going to space in the first place. And so if you design that in, thinking about the end user, what they're going to do with it into the very beginning, and then you can speed up your development cycle.
All right, very good. I also wanted to ask, so from an end-to-end system, knowing that you guys build many of these small satellites, right? As your architecture approach, what was the criteria for the actual system components, the avionics, right? How did you guys determine these we're going to build in-house because we want better control of the system?
Sure. So when at Planet, being an imaging mission and wanting to get more frequent access to space, we chose the 3U form factor, 3-unit form factor, 10 centimeters by 10 by 30. And so that was, and you know, engineers get creative if you're under a tight constraint, so that was the constraint that we always had to build with. And then we wanted to test the end-to-end system, so we used off-the-shelf components in order to do that from aerospace suppliers. So one was a microhard, for instance, an S-band, both transmit and receive capability. It's, you know, off the shelf, you can buy it from a component, you can put it together. We knew that we wouldn't be able to do that for an operational mission, because in an operational mission, it has to be in a different frequency that you communicate with your satellite as a commercial remote sensing system. It has to be an X-band. But in X-band, the only commercial radio that was actually available from Surrey. That was less than $1 million, I should say. But it was about the size of a brick. And being able to, and that wouldn't fit with then the telescope and everything else that we needed to do. So that was something that, because it wasn't available off the shelf, we knew we had to do that our own research and development along the way. So we built our own radio. We used other people's radio to begin with while we built the entire system. And then just every single build, that's what we call it, every 3 months or so, we see where within our entire system would have the nonlinear benefit that comes out, more data that comes out. And you know, for instance, between build 10 and build 12, we moved from AA batteries to 18650 batteries. And that ended up, and 18650 batteries, these are the batteries that are coming out of that will be coming out of the Gigafactory. These are in the Tesla. It's, you know, about this, it goes from the size of your pinky cut into the size of your finger, but that doubled the amount of power that we can store on board, which then put our spacecraft to then be power positive. So everything can be on the entire time. And that's relative, and power is always one of the limiting factors in any sort of satellite system. And then that just opens up a whole realm of possibility. One of the things that I do also want to mention about what can be disruptive with this speed and agility are the new types of missions that you can do, and the fact that you can be in more or less constant contact with your spacecraft for a low Earth orbit mission that allows for you to constantly be upgrading the ConOps of it with new software. And being able to, in some cases, actually do onboard analysis for what it is that you're actually collecting. So I think that there's going to be a lot more new missions that can become available when previous constraints, such as power and compute on board, can more or less be forgotten. Then that just opens up the trade space for what new mission possibilities actually could be.
All right, thank you. Just one last question for all three of you. So, you know, as we embark on these missions, what is the biggest challenge that the three of you see time after time, and how is it that you guys are, you know, addressing these? And the one that comes to mind is, you know, the spectrum, the launch delays, right? We're secondaries. We're not driving the launch date. Right?
It is absolutely launch, okay, in my opinion. Launch is the single largest barrier to innovation in our industry. We can get access to space, yes. That is great. That has made so many things possible. It is kind of a stopgap. As there are going to be more things in space, it would be, people want to go to the correct orbits rather than to good enough orbits. And that's the best way in order to operate in a sustainable way in space. So launch by far is the single largest barrier to innovation, and nobody really is doing it quite right yet on the small side of things. And we now see that there is a market for it, and that there are small and nano launchers that are under development, but none of them are operational. And when that does become available, that will open up much more, that will decrease that large risk that we actually have.
Okay. What about for you guys, Sir Martin?
I would completely agree with Robbie that the constraint on the development and the marketing, well, the market applications for small satellites is predominantly on the launch. It's not just the fact of the accessibility and timeliness, but it's also the cost, which then itself dictates to some extent how you approach the space segment. On a slightly wider issue, though, if I sit back and say, well, what is the biggest challenge that we face? Yep. I think that as we see spacecraft becoming more and more software-centered, then effective, timely and reliable software is becoming an increasingly expensive commodity. And so that is one of the areas which I think is we have to focus on.
Okay. And what about for you guys?
So I concur with both these gentlemen, but I would like to add from the perspective of a government space agency, one of the big challenges is actually the cultural challenge. We have had, 40, 50 years of doing large spacecraft. And there's a practice to doing large spacecraft and an approach and a risk posture and an understanding that is very ingrained in the large organizations and the policy institutes within the government agencies. So the title of this forum is actually very appropriate. This is a disruptive technology in the sense that it causes individuals who fund space missions to have to address a new way of looking at something. Can you do this mission with a small system? Should you do this mission with a small system? What is the value or risk posture to it? Very often we're looking at singular, large, billion-dollar spacecraft, and we do phenomenal science with those, and I'm very proud to be affiliated with an organization that does that. However, we can now start looking at tens, hundreds, thousands of small satellites acting as fleets and swarms to do equally interesting and valuable high-quality science and exploration, and that's a new way of thinking that we've never done before. It changes the risk posture of every mission has to work 100% to 990 of the 1,000 have to work 100%, and that's a different intellectual posture. The inverse to that is that as these new small companies are starting up and doing fabulous work, not all of them are taking solid engineering practices. They think they can look it up on the internet, buy a bunch of parts and put it in a box and fly it. And maybe you'll get your Sputnik moment, you'll get your beep, but if you're doing it to, do high-value imaging, you have to do solid engineering, which I know Planet's doing. If you're doing it for exploration and supporting different activities for government agencies, you have to do solid engineering, and I know Surrey is. But not everybody is. So I think there's also this false understanding that just because you can take the risk, you can be sloppy and cut corners, and you can't. So there's what's called non-recurring engineering. You have to do solid engineering, whether it's a big spacecraft or a small spacecraft. The value you gain on a small spacecraft is I can buy another small spacecraft with the same engineering for a very small cost. I can't buy another big spacecraft for a small cost, right? I can just print out a whole bunch more small spacecraft after I've done the good engineering. And that's where I think we're going, and that's why that's so disruptive.
Could I add?
Yes, one more.
Yeah, I just want to add one other point, which is a non-engineering point, and that is, as we've seen these very disruptive systems being proposed, we have to make sure that policy tracks it. I mean, policy always lags technology. But what we're seeing is the technology and the opportunities that technology is enabling is accelerating away from the development of policy. And I think that's going to affect all of us in due course and many others. As we offer new services, the policies have not yet caught up, and that will constrain the exploitation of small satellites and other similar things.
All right, thank you, gentlemen. We're going to go ahead and open it up for questions now. Okay, we have one in the front.
Firstly, congratulations for a good panel discussion, very stimulating, disruptive, maybe a little bit to some. I have a simple question. All three of you have worked with COTS, commercial off-the-shelf components, for most of the satellites you've been building. Big satellites, the huge things, are usually built with qualified, space qualified, and military qualified components. Where do you see the limits of the COTS that you're using, and when do you think, or do you think there will be, a transition on COTS also for large satellites?
Yeah, I can start. I would actually love to hear you guys also answer this too. So what is amazing is it's literally the spec sheets that are available today, and being able to see the testing, the rigorous testing that each one of the components go through, from thermal cycling to mean time between failure to whatever it actually is, and that these components are manufactured in lots of millions. Right? Some of the challenges of a specialty component that is military grade or that is an aerospace quality is that they're manufactured in lots of hundreds, and then you destroy 10, 20% of them through testing, and then you get one of them. And that just costs so much money, and in some cases you actually do take on a bit more risk. These components are actually extremely deterministic in their performance. They're very high quality, they're very ruggedized, and we have not seen any failures to our knowledge on the types of components that we operate. Then again, we operate in a very low Earth orbit, so it actually is shielded by the radiation environment quite significantly. And we do good thermal management on board, so we always are within the specs of each one of the components.
Yeah, I mean, I think building on the comment I made a bit earlier, there has been, over the last 2 decades, a fundamental revolution in manufacturing process. And that process now results in very, very low random failure rates. And so building on exactly what Robbie says, those manufacturing processes remove many of the issues. Then it boils down to a fundamental understanding of the COTS device and its suitability for use in a radiation environment in particular, and then making sure that you have the architecture around it to make it flexible and resilient. Is there a limit to how far you can use COTS? I don't think so, providing you have very knowledgeable selection.
Yeah, I would concur with both of these gentlemen. I think for low Earth orbit, we're not 100% there, but I think we can largely say that off-the-shelf parts can pretty much provide all the components needed for effectively any valid spacecraft or space use you would want to have. You can do that. As you go into more and harsher environments, higher up near the radiation belts and outside of the geomagnetic field of the Earth-Moon system, I think we're still going to have to go with much more diligent and stringent requirements. That doesn't mean you can't use COTS, designs, architectures, or even manufactured parts, but you're going to have to do a much more significant lot testing to actually select out the components that work. And in certain places, you really may want to still go with the mil-spec or space S-grade parts because, frankly, they can perform a function that may be not easily achievable or easily acquirable from a commercial off-the-shelf system. But in general, the revolutions happen. We're just kind of waking up to it. You can use COTS in space. They do all sorts of COTS in the International Space Station now. There's no problem doing that. Again, it's a shielded environment, but they're up there 24/7 by 365, and there's no problem.
Yeah.
Okay, I think we have time for another question or two. Okay, up here in the front, in the middle.
Hi, Jean-Dominique from Airbus Innovation. As orbital manufacturing advances, we'll reach a point when eventually you'll be able to 3D print your small satellite in space directly using material that are already on orbit and eventually with a powder that you just upload with launchers. So the requirements on the launcher will be much less stringent than it is today, and the demand for launches will decrease, so the cost of the launch should also decrease. So my question is, shouldn't we focus on making orbital manufacturing a reality as quick as possible rather than designing launcher for small sats?
Okay, you want to take that?
Yeah, if I make a quick comment, I mean, I think that goes back again to the comment I made in my opening remarks. I see at some point we're going to be launching essentially bags of sand or whatever it is on the launcher and doing the manufacturing in orbit, and that will change how you design the launcher and perhaps possibly the requirement for it. But I suspect that what we will see that there will be an increased demand for space infrastructure, and so there will still be the demand for the launchers. It's just they'll be carrying a rather different cargo.
One good example of that is we're developing a small kit version of a nanosat that we're going to send up to the International Space Station, and it's just all the raw parts. that the astronauts will assemble and then put into the dispenser and deploy overboard. One of the challenges with almost any spacecraft is it's designed to survive launch, which means it's got extra mass, it's extra rigid, it's got, you know, extra testing. We shake and rattle these things on the ground like crazy because we want to make sure they don't fall apart when you launch them. If you actually assemble them in space, they can become much lighter weight, much simpler, much less rigid structures because they're not enduring the same stresses they would during launch. So there's a great opportunity. I very much agree.
Okay, Robbie, 30 seconds and we have to.
30 seconds. So the last bit of your question was, can we do it instead of nano launch? And please, the answer is no. We really, really do need nano launch. But it's an and, so I don't think it's an either or. I think that there will be quite a bit of research and development on in-space manufacturing, and that is happening now, and that is being led by space agencies and those types of activities. I think at first the applications will be new and novel, different types of structures that actually that would not withstand launch, but absolutely we need nano launch for the industry. Then we should also simultaneously be doing the research and development on board for in-space manufacturing.
All right, thank you, and please help me thank the speakers.